All right, that last video was getting a little long, so I decided to just cut it off at about the 20-minute mark, and let's have a shorter video now answering the question we left off with. Recall, carbocations do rearrangements, so if you wanted to put CH2, CH2, CH3 on a benzene ring, you do that doing Friedel-Crafts alkylation. Because if you had this propyl chloride here and used AlCl3, you would get this isopropyl benzene due to our rearrangement here. So, how do you put a straight chain on here? What if I wanted to put 4 carbons, a nice butyl group, a normal N-butyl group, CH2, 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 CH3? How would I do that? Well, you do that by doing a Friedel-Crafts acylation followed by a Clemmensen reduction. Okay, cool. More named reactions. What have we had? We've had Diels-Alder. Now we've got Clemmensen. We've got Friedel-Crafts. Very nice names. All right. So, if you want to add a 4-carbon chain to a benzene ring, start with an acylation, a 4-carbon acylation, which means note you also need that carbonyl carbon as one of the carbons. If you had 1, 2, 3 carbons in your chain plus the carbonyl carbon, that's 4 carbons. Recall, with this acyl chloride, this acid chloride here with AlCl3, we are going to bond the carbonyl carbon to the benzene ring. So you would make the carbonyl carbon CH2, CH2, CH3. We'd have this beast here. And it turns out you can reduce a carbonyl to a CH2, as Clemmensen found out, with Zn parentheses Hg in parentheses. This is called amalgamated zinc. Amalgam means mercury, so amalgamated zinc with HCl and heat will reduce a carbonyl to a CH2. So this is how you can add this group on here. Benzene ring, acylate it to make an acyl benzene, reduce the acyl benzene with a Clemmensen reduction to the CH2, and now you have it. And because this didn't go through any carbocations here that could rearrange, you can put the long chain on the acyl group and then just reduce it to that long carbon-carbon normal alkane chain. Now this requires some pretty nasty conditions, some acidic conditions. If it turns out your molecules are going to decompose or HCl is going to cause some substitution or something happening somewhere else in your molecule and you need base conditions instead, you can use the Wolff-Kishner reduction. Wolff-Kishner will also take a carbonyl and reduce it using NH2NH2OH- and heat will reduce that carbonyl to a CH2. So either of these work. Note, it doesn't matter. These are the same starting materials, these acyl benzene compounds. Acid conditions, use amalgamated zinc to do the reduction. Basic conditions with hydroxide, use NH2NH2 to do the reduction. So while truthfully it doesn't matter which way you want to work it, if you had a choice, because neither one matters, go with the amalgamated zinc. Go with a Clemmensen reduction. Here's why. Clemmensen, HCl, hydrochloric acid, pretty cheap. You can get that amalgamated zinc. Now, mercury isn't the best thing for you, but this amalgamated zinc isn't too bad. Just watch what you're doing. It's not that expensive either. NH2NH2 goes by the name hydrazine, and hydrazine is used as a component of rocket fuel, which means this stuff here is actually pretty dangerous. Not only is it dangerous as a rocket fuel, it's a really toxic compound. It's a nasty compound in itself. Very toxic. So this is just more dangerous and more toxic if you use the Wolff-Kishner reduction. So if it didn't matter, acid or base conditions didn't bother you, go with Clemmensen reduction. It's a safer way to do it. It's probably cheaper too. If you can't have acid conditions, go with the Wolff-Kishner and base and be very careful. All right. And the last part of this video, you can do an intramolecular Friedel-Crafts. If you have an acyl group and it is tethered to a benzene ring, you just add AlCl3 and you can close that ring. An intramolecular Friedel-Crafts is going to make a ring bonded to the benzene ring, another ring bonded to there. Now, the question is, though, which carbon? We know that this carbon here, the carbonyl carbon, is what's going to be attached to the benzene ring. Which carbon of the benzene ring will be bonded to the carbonyl carbon? If you make molecular models, you will see that it can only be this one here, ortho to it. Ortho to the tether is where this carbonyl will bond, has to bond ortho. If you make the molecule, you'll find that it just can't stretch to the meta or the para condition or position when you only have 1, 2, 3, 4 carbons, including that carbonyl carbon, only 4 carbons in the chain. So 4 carbons in this chain, 5, 6 when you do that. So if you're making a 6-membered ring, 2 carbons from our benzene ring, 4 carbons from our chain, including the carbonyl carbon, it will only go ortho. It's in order to stretch this all the way to meta or para, the benzene ring would have to pucker, and you would lose aromaticity because the benzene ring wouldn't be flat anymore. So watch for these intramolecular Friedel-Crafts. It's a way to enclose another ring on a benzene ring. All right. So that's it for this video. We will then start next time with quite an intensive section on substituted benzene rings. So what we're going to get into next time is, all right, we've looked at what happens when you did these reactions. I'll go to that first page. When we did all of these reactions here on just a plain benzene ring. The question is, what if you wanted to do these reactions on a benzene ring that already had something on it? What if there was already a chlorine on here and you wanted to put a nitro group on here? Oh, what if you had something like methyl benzoate on here? If you had a benzene ring with a carbonyl OCH3 and you wanted to put a nitro group, what will happen when we want to do these reactions with benzenes that have various substituents already on them? We'll be looking at that in the next video.